Hello, my name is Joshua Taylor, and this is my lab report for Lab 2, the motion of a falling object. Here is the table of contents for my lab report. Introduction. So the purpose of this lab is to observe and analyze a falling object that falls somewhat slowly, which means air resistance affects it, and apply Newton's first and second laws to generate models of the motion displaying the effect of that air resistance. The models used to do so are both physical, with a falling notebook, and computational, with code. The lab successfully captures the effect of air resistance on a falling object, bringing it to a terminal velocity, which we'll talk about later. Relevant equations and principles. First of all, Newton's first law says that an object at rest or in motion will stay at rest or in motion unless acted on by an outside unbalanced force. And we quantify that with Newton's second law that says that the net force on an object is equal to the change in momentum over change in time. Rearranging and expanding that formula, we get the velocity update formula, which is bulleted. That'll be used in the code later, as will the position update formula, which is given here. And then the drag force acting on the system, we use a turbulent drag, which sets the drag coefficient proportional to the velocity of the object squared, and that drag force is in the opposite of the direction of the velocity, seen by the negative v hat. So we're going to start with a physical falling notebook and analyze its motion using Tracker. And then we're going to make two computational models of the notebook's motion, one that neglects air resistance and another one that accounts for it, and these are made on GlowScript. So the experiment, we drop a notebook, which is the system, and everything else is the surroundings. We drop it from rest as smoothly as possible so as not to impart any initial velocity. And we assume that gravity and drag are the only operational forces. Others, like gravitational force of other objects, are negligible. We extract the data using Tracker and import it into a spreadsheet. So here we have the video of my falling object. The length scale was set using the length of this notebook, and the initial position of the center of mass of the notebook is set to be the origin of the system. As we drop it, we keep track of the object's center of mass. We stop it 1 frame before it hits the ground because we only care about analyzing the free fall motion. We take the timestamps and Y positions generated by Tracker and put them into a spreadsheet right here. Then we can move on to the code section. We use the Lab 2 starter code and edit specific lines of code to generate the falling notebook without air resistance. And then we do the same process, but we add in air resistance and guess and check to find the appropriate drag coefficient B value. And we ensure that the drag force is opposite to the direction of the motion of the notebook. We input both sets of generated data into the spreadsheet. So here's the code without air resistance. Set the initial mass, velocity, the time frame that we want to analyze. The net force is only the gravity. And running this, you get the motion of a falling object, and its velocity increases linear over time and magnitude. Of course, it's in the negative direction. Here are the timestamps of the object, and here are the positions. And then with drag, the big difference is that there's a drag coefficient, and we add the force of drag, which is opposite to the direction of the motion of the object. Add that to the force of gravity to get the net force. And running this, we get another falling object, except that this time its velocity starts to taper off towards a terminal velocity. Take that data, put it into this spreadsheet, and that generates a graph. Here in this graph, you see the observed position in blue, the predicted position with drag in red, which is pretty identical to the observed position, and then without drag, you see that the object falls faster than with drag. So the differences display the effect of drag. Red and blue positions are nearly identical, and notebook slightly tilted in real life towards the end of the drop, and so that could explain a little bit of difference between the red and the blue lines. What does it mean? Well, the model with drag in coding predicted a terminal velocity, and that lies around 5.33 meters per second in the negative j direction. At this point, the net force on the notebook is 0 and the system is experiencing dynamic equilibrium. If the object was thrown with some initial velocity, we see that the terminal velocity would remain the same, around negative 5.33 meters per second in the y direction. So that's the same no matter what. And in conclusion, the drag force resists the motion of an object and consistently brings it to a terminal velocity. The terminal velocity is constant for an object regardless of its initial velocity. Thank you very much.